Okay. So the last lesson, it takes into consideration, it's a little bit different than the rest of the unit. It does kind of feel like a one-off piece to it, which is still important because as we move into the next outcomes, we're going to see it kind of pull in and be a part of that again anyway. So one of the things that we do need to kind of take note of and recall from previous things that we've done, and we've seen this in grade 10, it will have been in your grade 10 math, a little bit maybe in grade 9, but it's all of those exponential powers, so all of our exponential laws. So just to kind of get our brain back and thinking in that mode, there are a few of those that I want to go over and just give you some examples again. So when we think product of powers, that's the scenario where if I had x to the power of 3 and I times by x to the power of 2, okay, this is multiplying. What do I have to do with my powers when I'm multiplying same bases together?
Add them.
You betcha. We got to add them. Okay, so product of powers, you're multiplying same bases, you're adding your exponents. Well, quotient of powers is just simply taking the same scenario that we've got. We may have x to the power of 3 divided by x to the power of 2. Same bases we're dividing. We end up subtracting those powers. So really now, right? So this is, we subtract. Here we add. Then the next one you would have seen is if I give you x to the power of 3 over x to the power of 2, or x to the power of 3 to the power of 2, this is a power to a power rule. So what we end up doing with our exponents is we end up multiplying. So in this instance, I'm going to have 3 times the 2, which is going to give me 6. Power of a product rule would be a scenario where I have maybe x to the power of 3, y to the power of 6, and maybe the whole darn thing is to the power of 2. So all we're doing here is we are still, it's a power of a product rule. You're still multiplying. You're kind of distributing that 2 that's on the outer with both pieces with both powers on the inside. So really still multiplying, you'll end up with x to the power of 6, and you're going to end up with y would be 6 times the 2, which would be y to the power of 12 that we get for an answer. And then the opposite of that, this one is just dealing with a quotient where this one was a product. So the scenario looks pretty similar, just dividing. If I had, let's change this to a y on the bottom. So if I had x to the power 6 on the top, and I have y to the power of, say, 4 on the bottom, and I have it, not to a 6. Let's change this to a 2. So same thing, power of a quotient rule. I'm taking this 2, and it is getting multiplied to both powers inside the set of brackets. So this is really going to turn into x to the power of 12 over y to the power of 8. At least starting to kind of refresh your memory of what you got going on. Zero exponent. Anything to the power of 0 is always going to be 1. Okay, always. So anything you see to the power of 0 is always going to be a form of 1. If this happened to be negative and x to the power of 0, this would actually be representing a negative 1. The negative isn't to that power of 0, so it's not contained in there. So that's why we're going to get a negative 1. If I contained it with a set of brackets and the whole thing was to the power of 0, then that whole darn, because the negative is contained with the x to that power of 0, then that's going to make it up to equal 1. Okay, so the digit itself Okay, any value to the power of 0 will still give you 1. Now it's either if it's going to be positive or negative is basically what you've got as options there. Okay, negative exponents. Fun. Okay, so if I have x to the power of a -3, and I want to make that positive, that's the same as saying, well, if I take anything, I can always make it over 1. I can always put that as a, okay, any whole number, I can put it over 1 and put it into a fraction form to make it look like a fraction. So for me to make this a positive exponent, I am going to take what base is to that power of that negative exponent. That's the whole thing there. That's to that power of -3. And it is literally, I'm going to move it to the denominator. So really, in essence, I don't have anything left on top. I'm really dividing it out. It's really, I'm left with a 1 on top, and I move that x to the power of -3 down to the bottom. It now becomes a positive x to the power of 3 on the bottom. The 3 becomes positive. Same scenario as if I had something like 1 over x to the power of -5, and I want to make that a positive exponent. Because typically, if we want to work, we will always use and leave our answers with a positive exponent. We don't typically leave things with a negative power to them. So in this instance, again, it's the x to the power of that -5. It's going to shift up. So in reality, 1 over x to the power of -5 is the same as saying x to the power of a positive 5. Questions on that? Okay, the last one is fractional exponents. Now this is the one, we will use this one quite a bit through this lesson, so it's a good refresher for us to go through this. If I gave you x to the power of 2/3, we can rewrite this in terms of a radical, okay? So basically, in order to do that, this number in the bottom is going to tell us whether or not we're working with what kind of root. Are we dealing square root, cube root, fourth root, whatever that value is. So we know we are creating a root of some sort. The base always goes underneath my radical. The number in your denominator is the one that ends up in your index. So it's going to tell you, is it a cube root, a square root? Okay, so in this instance, this is a cube root. The 2, this is just a basic power, just like an exponent, like what we've been working with. So really, this is saying the cube root of x is going to be to that power of 2. So we can write it like that. Okay, that's one way to write it. Or it's still a cube root of x, but my x is being squared. So that base is being squared. So I can write it like this, or I can write it like this. Resulting answer, you'll end up with the same thing in the end. Is that okay?
Yes, I didn't remember that, but it looks good.
I know, that's one that we haven't probably seen since probably grade 10 math. That's one that but we do end up using it quite a bit moving forward. So this will be a piece that we'll watch for now. Okay, so now moving forward, now we get into the meat of this lesson after we kind of give ourselves a little bit of a refresher of all our exponential laws. When we look at an exponential function, and we've done throughout this whole unit so far, is we've looked at graphing exponential functions and whatnot, and we see them, right, with a 3 to the power of x, or we have a base of something, and it's always to a power of our variable of being x. If we look at exponential functions, we can write them in different ways, and we will be playing around with these over the course of the next couple of units and kind of converting them back and forth between various representations. But we can basically represent this. So in essence, we can get an equation like this: 3 to the power of x is equal to 27. And we need to figure out, well, what does x equal? So by looking at this, I'm basically saying 3 to what power is going to give me 27? And if we sit and we can sit and think about and go, well, 3 to the power of 1 is 3, and 3 to the power of 2, well, that's 3 squared would be 9, so it can't, x couldn't be a 2. Then we could get into, well, 3 to the power of 3, that would mean 3 times 3 times 3. That actually gives me 27. So if I looked at this, I go, oh, well, x will equal 3 to figure this out. That's all fine and good when we're working with somewhat easier numbers to figure that out, because really that's what this is saying, is that 3 to the power of 3 equals 27. Well, we can play around with this a little bit and say, hey, if we talk about this being a base of 3, maybe we can we manipulate the 27 and have it as a base of 3 as well? So in essence, what I would have here is I'd say, well, 27, if I wanted to rewrite 27 with a base of 3, I'd be saying, well, 3 to the power of 3 is another way of writing that, showing that 27, right? It's just another representation of 27. So what I end up getting here is that I get both bases to be identical, right, on either side of the equal sign. I've got a 3 on this side and a 3 on this side. Well, if both bases are the same, and we're saying that these have to equal each other, that must mean what is in the exponent also has to equal each other. So really, what we figured out is that x will equal 3. Now, you're looking at this going, well, yeah, we knew that already. That works when we're dealing with, right? It's easy sometimes just to see the equation and go, oh, I know what the answer is. Our exponential equations that we work with won't always be that easy where they're set up nice and neat and tidy like that, where we can just look at them at a glance and find out what that x value actually equals. In some instances, we might have x's on both sides. We might have, it'll be a little bit more complex than what we're working with. So in reality, what we're going to want to do is, if we can get and create same bases on either side of my equal signs, then what I can establish and do is set my exponents equal to each other, and then I'm able to figure out what my variable, what that x would actually equal. So that's kind of where we're moving to as we go through these questions. So let's look at the first one. It says, example, change the base of powers. So in this instance, it's saying write each expression as a power with a base of 2. Okay, so that ultimately, the 3 up here was our base. So essentially down here, we want our base to be a 2. And then it says, except for D, where we'll make it a base of 3. Okay, so let's play around with this. Well, if I look at 4 and I need to write it as a base of 2, well, 2 to what power will give me 4?
An exponent of 2?
You betcha. It would be an exponent of 2. So basically what I'm doing is I'm looking at just the 4 right now, and the equivalent of it with a base of 2 would be 2 to the power of 2. I still have that 3 out there, so I have to remember, oh, I'm still to that power of 3. All I did was rewrite the 4 here as a base of 2. So by doing that now, remember your exponent laws, I'm dealing with a 2 to the power of 3. I've got that power to a power rule. So this is really 2 to the power of 6. So when it's asked to write the expression as a power with a base of 2, I've got my base of 2. Once I've simplified my exponents, I've got a power of 6 on that. So the whole thing first is to rearrange, take whatever your base value is. You got to try to rewrite it as an equivalent with a base of 2. So in the second one, you've got 1/8. And I'm going to write it like this, just so that we can kind of see it visually, maybe a little bit easier as we move through this. Okay. So in this instance, I look at the 8 and I say, hey, is the 8, I need to write that 8 as a base of 2. Well, 2 to what power is going to give me 8? So in this instance, I'm hoping you're thinking 3, because 2 times 2 times 2. So 2 times 2 is 4 times another 2 will give me 8. So 2 to the power of 3 will give me 8. Here's the problem though. I just need this to, in the end, I really need this just to be a base of 2, not a 1 over 2 to the power of 3. I need it to just be a base of 2. So in this instance, how do I make this go from here to just having a 2 without the 1 and have a power of something? Well, I can rewrite this. This is a positive exponent down here, right? For this instance, I could actually move this whole thing up to the numerator, right? Moving up here. And by moving it up out of the denominator and moving it up, this would actually become a -3, which in essence, I would still have a 1 underneath, but I don't need that 1 under there, right? Because anything divided by 1 is still itself. So I really don't need that there. So really what I've got, I'm left with my base of 2 and my power to be a -3 in this instance. Questions? Okay, so let's try the next one. So the next one now, I've got 8 to the power of 2/3. So right off the bat, I want to try and get that 8. Well, I know the 8 already. We've already established that the 8, if I want to write it with a base of 2, that's the equivalent of saying 2 to the power of 3. Let me just make a line here. So I'm going to take that 8, rewrite it with a 2 to the power of 3, but it's also to the power of 2/3, right? It's got that additional exponent of 2/3 out there. So I've got that piece established. Then in the second bracket, let's look at what we've got going on. Okay, so really, I've got the square root of 16. Let's write this piece here, the square root of 16, as an actual with a base and a power to it. So right now I have a base of 16, and this is a square root. So that means my denominator has a little 2 in the denominator because it's representative of being a square root, not a cube root. And then it's got a power of 3 to it. So I really have a 3 above it. So this is really 3/2, 16 to the power of 3/2. And that looks really, really bad now. Okay, so now that I have that 3/2 there, and I've got the 16, but the 16, I need to make it as a base of 2. So this is, I can say 2 to what power is going to give me 16? Well, in this instance, 2 to the power of 4 is going to give me 16, and I still have to that power of 3/2 outside of it. Okay, so there's a lot going on in this question because I've got fractional exponents in here that I'm working with. I've got different bases that I've had to take a root and convert it into kind of exponential form, right? Before then taking that base and converting it to a base of 2. I'm getting a little bit felt a little messy there right off the bat. So there's lots of little pieces going on in there. Now when I look at this, because ultimately my answer still has to be just a single base of 2. Right now I've got a base of 2 here with a lot of business of some powers going on. I've got a base of 2 here with a lot of powers going on. We need to clean some of this up in here before we can kind of simplify it. So if I'm looking at this and I go, oh, I've got a power to a power. Well, I know my power to a power rule from above is I need to multiply my exponents together. So I'm going to have to multiply these exponents together. I'm going to have to multiply those exponents together. Now, I've got a whole number times a fraction. If it helps, put this as 3/1. Put this as 4/1. Okay, just because then when you're looking at a fraction times a fraction, you multiply your numerators together, multiply your denominators together. So then what I have is I've got 3 times 2 is going to give me 6/3. And in the second one, I've got 4 times 3, which is 12 over 1 times 2, which is 2. So you're starting to see how these are getting a little bit cleaner, getting a little easier to see. So now I can even make this a little. 6 divided by 3, that gives me a 2. And 12 divided by 2, that gives me a 6. I'm dealing with two bases that I'm multiplying together. I want to make it a single base. I need to add my exponents together. So in this instance, I'm going to have 2 to the power of 8 as my final answer. So the reason we're doing these questions is just to get our brain in that mode of having the ability to transfer, to change a base to a different base and writing an equivalent base to it. That's what we're doing with these questions. So in some of these, like I said, they start to get a little messy, but sometimes some of your practice questions, I want you to have experience at all sorts of types of questions that you've got going on here. Okay, questions on that so far? Okay, so one more. This is going to be a good one. This time though, it's a base of 3. So we're not writing it with a base of 2 anymore. So this one we have to think about, 27. We want to write it as a base of 3. Well, we know from previous that 27 is the equivalent of saying 3 to the power of 3. And then I still have it to the power of 1/3, that 1/3 that was out after it. Okay, now I've got this 81. So same thing, if you want to rewrite this, so rewrite this as a fractional exponent happening here. When you get these roots like this, change them, rewrite them as a fractional exponent. So I've got a base of 81. Again, I'm going to have a fraction. This is my power, so that's my 2. That goes on the top in my numerator. And the bottom, my index, it's a cube root, so it's a 3 going in there. So I really have 81 to the power of 2/3. Now, I have to think about the 81. And I need to write it as a base of 3. So now I have to think to myself, 3 to what power is going to give me 81? Well, if I think 3 times 3 is giving me 9, times another 3 gives me 27, times another 3 is going to give me the 81 that I need. So in this instance, I know that 3 to the power of 4 is going to give me the 81, and I still have it to the power of 2/3. So same, very similar to what we did with the last question now. I've got this power to a power rule, and I'm going to take these whole numbers and put little ones underneath them just so we don't get confused of where that 3 is getting multiplied to. So I've got 3 to the power of 3 over 3, which is actually the equivalent of 3 over 3 is the equivalent of 1. In the second one now, I've got a 3, and I've got 4 times the 2, which is 8. 1 times 3 gives me 3. I've got that lovely business going on. Now, same basis. I need to take my exponents and I need to add them together. So in this instance, I'm going to have 3 to the power of 1 plus 8/3. Well, not so easy on this score because now I've got a whole number and I've got a fraction that I need to add together. Well, I could make these to be common denominators, right? So in this instance, if I want to make a common denominator of 3, I can change this as 3 over 3, okay? Because 3 over 3 is the equivalent of having 1. So if I have that, I've got 3 plus the 8, which would make me 11 over 3. And that is my final answer. Lots of little pieces, things that we need to remember from previous math classes that we've got, especially the adding fractions, right? That comes back into kind of, have to refresh our memory on that. But the processes themselves stay the same throughout all of it, right? Get your bases to be, we're trying to get, in this case, to get them to be 3s. And then from there, using our exponential laws that we've got along the way to help us kind of simplify and get her down to one single base to it. How are we on that? Cruz, where are you at?
I believe I get it.
Okay, Winnie, how are you doing?
Can you teach like how you get the 11/3 again?
In here? So if I think about this as 1 plus 8/3, right?
Mhm.
So if I treat this as 1 over 1, essentially, right? Because I put any whole number over 1. Now, in order for me to add fractions together, I have to make a common denominator. So in this instance, I would want to make a common denominator of 3 here. So now I have to think to myself, well, how do I get from 1 to 3? What do I have to multiply by? Well, I have to multiply the bottom by 3. But the moment I multiply the bottom by 3, I have to multiply the top by 3 as well. So in this instance, that's why I'm getting 3 over 3 plus 8 over 3. Now, adding fractions, you're just adding your numerators together. That's what's giving you the 11, and then you carry that common denominator, and that's where you get the 3. You do not add the denominators together. It stays as just a 3.
Okay, thank you.
Okay. Okay, good. Kylie, how are you doing?
I think I'm okay.
Okay. Okay, just stop though if you've got questions.
I think I'm following it too, so I can review with her after if we need to.
Okay, perfect, perfect. Okay, so now what we're going to do is actually put into practice all of these pieces that we've learned already to actually solve an exponential equation. Okay, so here's a perfect example of one where we're given 2 to the power of 4x is equal to 4 to the power of x plus 3. Okay, so you've got this lovely equation set up. Our variables happen to be up in the exponents, okay? And that's hence why it's an exponential equation. So our task then, just like what we've been doing, is we're going to need to, and kind of remember when I was talking up here, it's like, oh, well, if we get an equation and we are able to make the bases on either side of the equal sign, if we can get them to be identical, then we can essentially take our exponents, set them equal to each other, and we can solve for our variable that we've got. So if we look at what we've got down here, I've got a base of 2 and I've got a base of 4. So my goal moving forward is I need to be able to, can I make these bases to be identical? Well, when I look at the 2 is already pretty small. It's pretty condensed already. So I look at that and go, I'm not doing anything with the 2. Okay, I can't simplify that anymore to get me to anything easier. But the 4 now, I have to ask myself, well, if I can't simplify the 2, can I get the 4 to a base of 2? Because if that works, that's what we want to do then, right? So it's ideally, we're always trying to kind of recognize what we can see to make same bases. So in this instance, I can take that 4 and I can write it with a base of 2 to the power of 2 to mean the same thing. So this 4 in here is the equivalent of saying 2 to the power of 2. I still have that x plus 3 out there. Okay, so all I've done is I'm just replacing that 4 with a 2 to the power of 2, just so that I can get these bases to be identical. So now what I got, I'm going to rewrite the left-hand side, because that one I haven't done anything. There's no manipulation to it. It is what it is. This side, though, however, I've got this 2 to the power of x plus 3. Well, this is the same as saying, I'm really can rewrite this as, well, that's the same as saying 2 times that x plus 3, right? Like that's what it means. It's still a power to a power. I've got this exponent out here to this exponent. So I'm just multiplying them. So that's all I've shown here is that I'm showing that the 2 is getting multiplied to that x plus 3. So here's the good part. We've got same bases now because we're basically saying this side equals this side. Well, if the bases are identical, that must mean our exponents are going to have to equal each other. So that means I can literally take the exponents that I have set them equal to each other. Oh. And then what I've got is just a lovely equation that I can go ahead, gather my variables together, and solve for x. So in this instance, I'm going to take the 2, because I want to multiply that through. I want to distribute that. And that's going to give me 2x plus 6. And then, got to get my x's together. I've got to get them all over to the one side. So I'm going to subtract the 2x over, which is going to give me a 2x is equal to 6. And then my last task, divide both sides by 2. And I get x equals 3. And in theory, you should be able to check all of these questions to see if you've done them right. In theory, you could take this 3. If you plugged it back in for your x on both sides, what you get for a value over here should equal the value that you've gotten on this side. So you've got an easy way to kind of go back and see if what you did, if you've done it correctly, your answer will actually hold that equation true in the end. How does that feel? Okay, so let's take a look at the next one then. You've got 9 to the power of 4x is equal to 27 to the power of x minus 1. Same scenario, right? You're still got to try and figure out what is a common base that you're contending with. I look at this and go, well, 9 and 27. My brain automatically, you're going to start to see there's going to be some common values that start popping up, right? So always take your smaller number and see if you can reduce it. Is there a number that, a base that to a certain power that would give you 9? And I hope in this instance you recognize and go, oh, yeah, 3 squared is the same as saying 9. So you could look at it that way. But now, remember the 27 we did earlier, we can also make that to a base of 3, and we can say, hey, 3 to the power of 3. And that is to that power of x minus 1. So you're going to have to play around and get a little comfortable with some of those you're going to see some common numbers that are going to pop up every once in a while that you'll be more.
For the most part, are we always going to have bases that are easy to find the common base with these, or does it get squirrely?
For the most part, they're going to be pretty standard. You're going to recognize the numbers. For the most part, I always check your smaller number and see if you take that base of your smaller, like the 2 over here, for instance, right? I know that I looked at that and went, oh, well, 2 to the power of 2 gives me 4, right? So if you're able to take the smaller one and put it to a power to get your larger, right, the other base that you're working with, that's the easiest way to check first, okay? This instance, there is no 9 that to a power of something will give me 27. So I know in that sense, I'm going to have to start breaking my numbers down, right? Both numbers are going to need to get broken down. And so in this, I look at, I start to see, I know 2 to no power is going to give me 9, right? So then I have to use your smaller number to see if you can find a common base that would work for both of them. Okay, so now we're back to that power to a power rule instance here. So I've got, this is the equivalent to saying 3 to the power of 8x. And this side over here, this is really the saying 3 times that x minus 1. And again, you've got established same bases on either side of the equal sign. So I'm really focused on just my exponents now that I can set equal to each other. So I've got 8x is equal to 3 times x minus 1. So just like before, we're going to distribute through. And then I'm going to subtract the 3x because I want to get my x's to the same side. And I'm going to get x is equal to -3/5. And you're going to get that. They're not always going to work out to perfect lovely numbers every single time, but so don't fret when you get something that doesn't quite work out the way you thought it should. But again, you can throw it in, use your calculator, do a double check to see if your answer works out. Okay, I'm just looking at the other ones. Do we feel like we need to do another one of those, or how do we feel?
Helping us to
You guys call it. We can do another if you want to just try one.
We're just finishing writing down the rest of the notes there.
Fair enough. I'll give you a moment. Cruz, how you making out?
Yeah, I'm just finishing the rest of the notes.
Okay.
I'm just
Okay.
copying it down.
Okay.
Well, honestly, if we're all here, then it wouldn't hurt to do another example. I know I don't have anywhere to go.
Funny thing, either do I. Okay, so let's try another one. Did you guys, Winnie, how are you making out?
good. Can you help me how to do like the checking thing?
Oh, for sure. So basically what I would do here is if I wanted to take that x to the power of -3/5, I'm going to go back to my original equation that I've got going on. So I would go 9 and I would go 4, but now instead of the x, I'm going to put in the -3/5 in there, right? And then I'm going to do the same thing on the other side, and I'm going to put in a -3/5 minus the 1. So what I end up doing here is I would look at this and go, oh, this is the same as saying -12/5. And on this side, I would have 27. Again, remember we're minusing 1. This is the equivalent of saying 5/5, which is going to give me a -8/5. So what I would suggest doing with that at that point is plugging this into your calculator, right? And making that, and then plugging this side into your calculator. So you're going to have to use your, you'll have this, is it this button on your calculator? Just a power button, right? That you can plug in and see both sides equal each other. That was a bad one. We should have used the other one as your example. Fractions are kind of nasty to look through. I know some people, if it's just a pure check, you may even want to change this to a decimal and plug in the decimal and work your way through that too, Winnie, right? Like you can go through and there's different ways to do that. Okay, so let's have a look at one more. Which one? I guess it doesn't really matter which one we work with. Okay, so if we look at 4 to the power of x plus 2, and we've got it equal to 64 to the power of x. So your biggest thing now is to identify what base are we going to work with moving forward. And so this is I'm kind of curious. Let's see how, I'll give you a moment to see if you guys can figure out which base you want to work with. And I'm wondering if there's a couple options here for us. I think there's a couple different ways to approach this, and I think we can all get the same answer.
4 and 2.
So a base of 2?
Or a base of 4.
Or a base of 4?
Yeah, I assume you'd always want us to go with the lowest reduction, so you'd want us to use 2 and not 4?
No, absolutely. And that's why I looked at this question and my brain went, oh yeah, convert them to 2. But then I just did a quick calculation in my head. You can do that if you recognize that you can take 4 and go 4 to what power is going to give me 64, then do less breaking down, right? Like if you can recognize and see that 4 will also work, use it. You don't have to break both sides down. So here, I'll show, let's do both ways just to show you that it actually works that way. So if I treat this as, if I stuck with same base of just using 4, the 64, the equivalent of that is the same as saying 4 to the power of 3 to the power of x. Really what I've got going on here is I was able to get same bases really quickly because I only had to break the one number down, not both of them. And then in this instance, I can take my powers, set them equal to each other, solve for x, and I find out that x equals 1. So if I did this exact same thing now, but did a base of 2, well, a base of 2 for the 4 would be the equivalent of saying 2 to the power of 2. And I would have 64. This is where there's a breakdown a little bit more. That's the equivalent of saying 2 to the power of 6. Okay, and that would take some figuring and some calculating. You just keep 2 times 2, and then that times another 2, and times another 2, right? You keep going until you get 64. This is a mix up here. So same thing, I've got a power to a power, so I would have, and then I set my exponents equal to each other. And distribute. Might be a little bit more work with breaking them down into the smallest because you've had to convert both sides of this. But ultimately, in the end, you end up getting the exact same answer.
Well, I just doing our math class with Kylie. You are just way back like 10, 15.
So that one works out. Okay, do you want to try the last one?
Sure.
Yeah, it could be. Yeah.
Okay, everybody went super, super quiet there. I was wondering where everybody went. Okay. Okay, let's try the last one. What's our base going to be for this one?
So basically,
4 can go into both.
no, because
Oh wait, of 2, I guess, because the exponent. Yeah.
4 to the second power would be 16, right?
Yeah. So yeah.
Yeah, that's the thing here. Like our brain thinks there's got to be something similar between 4 and 8 because we look at them and go, okay, yeah, they're so close. Yeah. But if I was going to use base of 4, yeah, this one sure would stay the same. But this one, there's no way that I could take 4 to a power to give me 8. Because, right, 4 to the power of 1 gives me 4, but 4 to the power of 2 would take me right to 16 already. So it would go past 8, right? So I can't use the 4. But you're right, 2 certainly would work. So I could replace the 4 with 2 to the power of 2, and I still have that 2 to the power of x outside of that. And then the 8 is equivalent to saying 2 to the power of 3, and I would still have that 2x minus 3 out front. So same thing as before. I'm still, power to a power rule. I can rewrite this. And then take those exponents, set them equal to each other. And distribute through. And then my last step here is to solve for x. So in this instance, because I have more, my 6 is my positive number, I'm going to move my 4x over in that direction. And you're probably thinking, wait a minute, everything is over on that side now. But I like the fact that I have that positive variable there. So then all I'm going to do is add my 9 over to the other side, and I get 2x is equal to 9. And then I'm going to divide both sides by 2, and I get x is equal to 9/2. So a lot of these ones, they become very repetitious, right? It's the most difficult part in these is to establish the fact of what base am I going to convert them to. And once you can get that kind of under your belt, then the rest of it uses some of your exponential laws to kind of identify what that and figure out what the answer of solving for x is. Questions on that? Okay, well, that's it. That's all there is to this lesson. So we basically are kind of gotten through the meat of outcome 9C now. So basically you've got the rest of, I think that's assignment 3 in your assignment package in your notes. You've got that you can play around and work through. There's some review questions in there to play around with. And you also on Google Classroom now, I'm just going to stop sharing this. Are you guys, did you get the answer down for this? Before I take it away?
I have it.
Winnie, did you get it?
Which one?
I got it.
Okay. Kylie?
Yep.
Okay. Okay, I'll stop sharing that then. So basically then what we will end up doing then is Thursday, then we won't start a formal lesson. Then I think what we will do is I will come online on Thursday at 1. If you've got questions as you're working through your review, if you want to have answered, you want me to go over something, then we will take that time to do then. Okay, so it's not a mandatory you have to come online on Thursday, but if you want and you need some questions answered before, if you're choosing to do the test on Friday, then I'll be there.
Cool.
All right.
Does that work?
Yep.
And know that even before then, if you're working through something and you have a question, just ask, right? Throw me a text and remind and ask away. I don't mind answering questions, okay? It's just a steady, I've got calculus kids that are coming online and they're working through questions and I'm answering all the time. So don't feel bad. That is exactly what I want you to be doing. So don't let it sit and wait till Thursday when I could easily help you in 5 minutes and get you back on your track, on your way, okay? Okay, do you guys have any other questions?